Concavity. In this lesson, we'll be learning about where a graph is concave up, concave down, and points of inflection. So we'll be looking at the curves of the graph, and we'll be looking at the equations in order to find where a curve could be concave up, where it's concave down, and its points of inflection. So a curve is concave up if it's above its tangents. So you can see here on the graph on the right, sometimes we say, could this section of the graph hold water? If a graph is concave down, then it's below the tangents, and we could ask ourselves that this section of the graph cannot hold water. Inflection points are points at which the graph changes from concave up to concave down. And this inflection point is determined by taking the second derivative and making that second derivative equal 0 and solving for x. So in this graph, you can see that there are sections of the graph that are concave up in red, and the green section is concave down. We also have identified points of inflection. So the section that's concave up is from the x values of -1 to 1 and x values from 3 to 5. It's concave down with having the x values 1 to 3. And the points of inflection are at 1, 3 and 3, 3 at those ordered pairs. So here we're asked to determine the concavity and points of inflection from this equation. So what we'll need to do is we'll need to determine the second derivative. And if the second derivative is greater than 0, then it's concave up. If the second derivative is less than 0, then it's concave down. And when the second derivative equals 0, then we've determined the inflection point. So if we take a look at the equation, the first derivative becomes 3x squared minus 18x plus 24. And I do the derivative again for the second derivative, it becomes 6x minus 18. So in order for me to find the inflection point, I take 6x minus 18, make it equal 0, solve for x, and x equals 3. So if I take the value x equals 3 and substitute it back into the original equation for x, I get 3 cubed minus 9 times 3 squared plus 24 times 3 minus 20. And when I solve this, I get a y value of -2. So you can see that I've sort of sketched on a graph my x value of 3, and I've placed the ordered pair 3, -2. That's where the point of inflection occurs. And I determine the inflection point by substituting my critical value with the second derivative into the original equation. So now I'm going to pick checkpoints on the left and the right of x equals 3. And I pick the ordered pair 4. And when I substitute 4 into the second derivative is positive. So it's greater than 0, so it's positive, so it's concave up if it's positive. My x value on the left side of 3, I chose 0. And when I substitute that into the second derivative, I get a negative value of -18. So my second derivative is less than 0, so that's where it's concave down. And you can see that I've sketched a graph where the curve would be concave down, the inflection point, and then where it's concave up. So you can see that it does resemble the shape of a cubic graph. Here I have another example where I'm given an equation and it has an inflection point of 1, -6. And we're asked to find the value of b. So all we know to do so far is we know that we have to find the second derivative, because that's what we use to find concavity and inflection point. So I'm going to go ahead and take the second derivative, which equals 6x plus 2a. And for the inflection point, the second derivative equals 0. So I make this equal 0. I sub in my x value of x equals 1 and solve for a. So using my algebra skills, I get the value of a equaling -3. Now I have a equaling -3. I have an ordered pair 1, -6, which takes the place of x and y. So I'm going to sub in these values into the original equation. Y equals -6, x equals 1, and a equals -3, substituting them all into the original equation, making my calculation b equals 0. Here I have another example. I have a graph which equals -5 over x minus 2, and it says it's concave downwards for which values of x. So if it's concave downwards, that means that the second derivative is less than 0. So in order to take the derivative of this equation, I'm going to bring x minus 2 into the numerator. So I'm going to place brackets around x minus 2 with the exponent 1, and if I bring it into the numerator, the power is to the -1. Take the first derivative, subtract 1 from the exponent, and then take the second derivative, gives me -10, bracket x minus 2 to the power of -3. And if I'm going to make the -3 positive, so I'm going to bring x minus 2 into the denominator. So my final derivative is -10 over x minus 2 all cubed. So if this graph is concave down, when the second derivative is less than 0, I have to make -10 over x minus 2 cubed less than 0. And if it's less than 0, that means that it has to be negative if it's less than 0. And I notice that I have -10 in the numerator, which is already negative. So a negative divided by something in the denominator, it has to be positive. X minus 2 all cubed has to be positive in order for my result to be less than 0. I take the cube root of both sides, so the cube root of x minus 2, because I'm just using my algebra skills. And my final result is that the values for x have to be greater than 2 to make it concave down. If all the values of x are greater than 2, then my second derivative is less than 0. And you can see here that I've sketched the graph. And if you look at the x-axis, greater than 2, you'll see that the curve is concave down.